All right, today we are going to go over acid-base titrations. Titrations are a lab skill. You will often do a titration in a lab, and then you're going to have to solve the problem from there. So an acid-base titration really involves an acid-base reaction. We have to make sure that we understand what's happening in these reactions prior to doing the problem with the titration. In an acid-base reaction, we start with an acid, and remember that acids are substances that contain H+ ions. So I have an acid right here, HCl, and I'm going to react that acid with a base. My base is sodium hydroxide, and I know it's a base because it contains that OH- ion. So I'm going to treat this like a normal double replacement reaction. Remember that when you are predicting the products, you can only put positive and negatives together. Never two positives, never two negatives. And in a reaction, we always have to make something new. So my hydrogen can pair up with my OH. I check my charges, +1, -1, that's stable. And then my Na can pair up with my Cl. Again, I'm going to check my charges and make sure that it's stable. Now that it's stable, I'm going to balance it. When I count the number of atoms on each side, I see they're already equal and this is balanced as written. Because an acid always contains H+ and a base always contains OH-, one of the products of an acid-base reaction is always going to be water, HOH or H2O. It is okay to write it either way. The second product is always going to be an ionic salt. In this case, sodium chloride, NaCl. Well, because water has an H and an OH ion, this is going to be a neutral product. My NaCl has no H's and no OH's, and therefore it is a neutral product as well. This is true whenever you react a strong acid with a strong base. You will end up with two neutral products. One of those neutral products will always be water, and the second will always be an ionic salt. Because we end up with neutral products if we add exactly enough acid and exactly enough base to cancel out, our products are neutral and the pH of our solution will therefore be 7. These acid-base titrations are known as neutralization reactions. So in these neutralization reactions, we have to make sure that we add exactly enough acid to react with the base that's there, or vice versa. We want to make sure that all of the acid is used up and all of the base is used up so that both of our products are neutral and we have no excess reactant. Let's look at an example in which we set up a titration and then we're going to do the math that goes along with it. So in a titration, there's some specific equipment that we use. The first is something called a burette. A burette is used to measure liquids very accurately. There are measurements or tick marks on these, much like you would see with a graduated cylinder. All right, we are going to fill our burette with a known concentration of our acid or base. In this example, we're going to put our base in there, our NaOH, and we are going to use a 0.1 molar solution of that NaOH. We are going to fill it up. Now, something interesting about a burette is that they read backwards. So these are a little bit different than a graduated cylinder. When your burette is filled, it will read at 0.0 milliliters. You are measuring not the amount that the burette holds, but instead you are going to keep track of the amount that you add to the reaction flask below. The next part of the setup is to put our acid in the Erlenmeyer flask. When we put our acid in the Erlenmeyer flask, we need to keep track or measure exactly at what volume we put into the flask. I'm going to put 10 milliliters of H2SO4 in here. The problem is I don't know what the molarity or concentration of that H2SO4 is. That is my end goal, to figure out what is the molarity of the acid in this Erlenmeyer flask. Now the goal of this is to add exactly enough NaOH from the burette in order to neutralize my H2SO4. The problem is that I can't see when all of my H2SO4 has reacted with the NaOH. So instead, we're going to add something called an indicator. An indicator is a substance that changes color at a specific pH. When we add our indicator, we would just add a couple of drops of indicator into our H2SO4 before we begin adding the NaOH. Again, the goal is to add exactly enough NaOH to react with the amount of H2SO4. We'll then be able to use the data that we collect in order to determine the concentration or molarity of our H2SO4. All right, step one of a titration problem every time is to write your balanced equation. When I write my balanced equation, I always want to make sure again that I pair a new positive and a new negative together in order to make my compounds. Notice that when these are reacted, I've made water, which is always one of my products, and Na2SO4, an ionic salt. I need to keep track now of the numbers or the amounts that I've used in my titration reaction. One strategy that I find to be very helpful here, since you have so many numbers and so much data, is to write what you know about each substance underneath the substance in the balanced equation. So my NaOH, I know a little bit about my NaOH. I know the molarity is 0.1. The H2SO4, I don't know the molarity. That is my end goal. But I do have one other important piece of information. I know that I measured out exactly 10 milliliters of that H2SO4. Milliliters is typically not helpful when I'm dealing with solutions. I need liters. So I am going to convert my milliliters into liters right off the bat, knowing that 1,000 milliliters is equivalent to 1 liter. I know that I have 0.10 liters. In order to figure out the molarity of the H2SO4, I need to start adding NaOH to my reaction container below. You'll notice that there's a little valve here, and if I turn that valve, it's going to allow the NaOH to flow from the burette into the reaction container. Now remember that we did put an indicator down here, so we are watching for the moment that the solution turns color. So typically phenolphthalein is one of the more common indicators, and you would watch for a color change to pink here. So I continue to add my NaOH to the reaction container and swirl. I want to keep doing this until the solution down here changes color. When that solution changes color, that's when I know I hit the point where I've added exactly enough NaOH to fully react with my H2SO4. When I do that, I want to make sure that I get a measurement on the burette. I know that my burette started at 0 milliliters, and when the color change happened, it ended at 24.48 milliliters. I really don't care where it started or where it ended. What I do care about is how much I had to add in order to reach that neutralization point. In this case, because we started exactly at 0 on our burette, it's easy to read. We just take 24.48 minus the 0.0, which obviously gives us 24.48 milliliters of NaOH used to hit the neutralization point. Now, if you did not start your burette exactly at 0 milliliters, that's okay. You would still do the same thing. Take your final minus your initial volume in order to determine how much you used. We now have one more critical piece of information, the volume of NaOH needed to hit the neutralization point. Notice that I converted my milliliters of NaOH to liters in the exact same way I did for the acid. We always want to make sure that when we are dealing with a solution, we are using molarity and liters as our units. Now I want to take a look at the information I have. I have everything I need to solve the problem, but before I solve, I want to come up with a plan. If I know the molarity and I know the liters, I can find the moles of NaOH. Remember that our equation molarity equals moles over liters helps us determine the concentration of any solution. So if I know the molarity and I know the liters, I can find the moles. Next, I want to keep track of what my end point is. My end goal is to get the molarity of H2SO4. So if I want molarity and all I have is liters, the one piece of information that I'm missing about the H2SO4 are the moles. If I can find the moles of H2SO4, I can solve this problem. Now, it's important to remember that moles of any two substances in a balanced equation are related through the mole ratio. So now I can connect this. My first step is to find the number of moles of NaOH. If I know the moles of NaOH, I can use the mole ratio from the balanced equation to find the moles of H2SO4. Once I have moles of H2SO4 and liters, I can determine the molarity or the concentration of this unknown acid that I started with at the beginning of the problem. All right, I'm always going to start with the substance that I know the most information about. I know the most about my NaOH. I know that molarity, moles, and liters are all related through my equation here, so I'm going to substitute in and solve. My molarity is 0.1, My moles I don't know, so I'm going to call that X. And my liters are 0.02448. Now I can solve for X, and I find that X equals 0.002448. It's important to keep track of my units here. X is representing my moles, and specifically my moles of NaOH. So I now have this number right here. If I know my moles of NaOH, I can find my moles of H2SO4 using the ratio from the balanced equation. I'm going to set up a dimensional analysis problem, and I know according to the equation that for every 2 moles of NaOH, I need 1 mole of H2SO4. Now I know that I have 0.001058 moles of H2SO4. I now know this number here. If I know the moles and I know the liters of my H2SO4, that means that I can now solve for molarity. So I'm going to use my molarity equation again, but this time I'm going to use it for my H2SO4. My molarity equals moles over liters. I'm going to substitute in what I know. I know my moles and I know my liters. I can then divide in order to solve for my molarity, and when I do that I get 0.106 molar H2SO4. So I was able to use the titration setup in a lab in order to determine the concentration of an unknown acid. In order to do that, I added enough base to hit the neutralization point. Once I hit the neutralization point, I recorded the volume that was necessary, and I was able to solve from there. All right, let's look at one more example. In this example, all of the information is presented to us in a data table rather than through the lab setup that we used in the last problem. But our steps are going to be exactly the same. We always need to start by writing a balanced equation. When I write my balanced equation, I know my products are going to be H2O or HOH and NaNO3. So again, this is a neutralization reaction. I have water and an ionic salt. The next thing I'm going to do is list everything I know about each substance underneath the substance that it pertains to. In my data table, it tells me that the molarity of the NaOH is 0.1. The initial volume in the burette is 1.80 milliliters, and the final volume in the burette is 44.95. So in order to find out the amount used, I'm going to have to subtract the two. When I subtract, I find that I used 43.15 milliliters of the NaOH. Milliliters are not helpful, so I'm going to divide that by 1,000 in order to get my liters, which is 0.04315. The last piece of information that I know pertains to my HNO3. I know the volume of my HNO3 is 15 milliliters, but again, I'm going to divide that by 1,000 in order to get that into liters. Don't forget to identify your end goal in the problem. The end goal here is to find the molarity of the HNO3. Now that I've organized all of my information, I'm going to come up with a plan. If I'm trying to find the molarity of HNO3 and I have liters, the only missing piece of information is moles. If I can find the moles of HNO3, I can solve the problem. If I look to the NaOH, I know molarity and I know liters, which means that I can solve for the moles with the information given. The moles of any two substances are related through the ratio in the balanced equation. That means that I have all the information I need to get started. When I start the problem, I'm going to start with the substance that I know more information about. In this case, I know more about the NaOH, so I'm going to start with the NaOH, and I know that molarity equals moles over liters. I'm going to substitute in what I know. My molarity is 0.1. My moles I don't know, so I'm going to call that X, and my liters are 0.04315. Now I can solve for X. X is equal to 0.004315, but I need to keep track of the unit and the substance. This is moles of NaOH. So now I know this number here. If I know the moles of one substance, I can find the moles of any other substance in the equation using the mole ratio. In this case, the coefficients tell me that the mole ratio is a 1-to-1 ratio. I'm going to use that ratio to convert my NaOH into HNO3. Notice that when I put my mole ratio in, my units of moles of NaOH cancel out. It is important to show this mole ratio step even when the mole ratio is a 1-to-1 ratio. When I solve, I find that I have 0.004315 moles of HNO3. I'm going to write that up here, and now I know my moles and my liters of HNO3, which means that I can solve for my unknown variable of molarity. So now I'm going to do my molarity equation again, this time for the HNO3. I don't know the molarity, but I do know my moles, 0.004315, and I do know my liters, 0.0015. I can take my moles over my liters. When I divide, I get 0.288. Remember that this is the molarity of HNO3, and I need to label it as such. So I was able to determine the molarity of the HNO3 through the data given for the titration. I hope that helped to clear up some of your questions with acid and base titrations, as well as those neutralization reactions. Don't forget to like and subscribe, and thanks for watching.